Hello again. This lesson we're going to look at section 1.9. We're going to continue on the idea of a linear transformation and look at the matrix of a linear transformation. So last time we saw the idea of a linear transformation being the kind of a function or a transformation that had two properties. One is where you can add things together first and then transform, or do it the other way around. And the second one being where you can multiply and then transform, or the other way around. So here's an example. Suppose you have a linear transformation. So I'm not telling you here what the linear transformation is. But what I am telling you is the result of two transformations. I'm saying if I take the vector 1, 0 and transform it, I get that. If I take the vector 0, 1 and transform it, I get that. And now I'm saying, well, what does this mean for a general one? If I just have any vector at all, x1, x2, is this enough to tell me how it works, what the transformation is? And the answer is going to be yes. With just two examples, and the fact that we have a linear transformation, I can use those two examples to figure out everything. So here's what I'm going to do. I'm going to use the fact that t of u plus t of v is equal to t of u plus v. And in particular, I'm going to expand even further, where c1, a constant times that, plus a second constant times t of v, is equal to t of c1u plus c2 times v. That's the idea of linearity. I'm going to use that. So I have these two vectors I'm starting with, 1, 0, and 0, 1. What I'm going to do is figure out a general equation, how I combine those two vectors to get my x1, x2. And we're just going to note that x1, x2 is equal to x1 times 1, 0 plus x2 times 0, 1. Okay? Now, if those two things are equal, I can transform the entire thing. So the transformation of x1, x2 is equal to the transformation of x1 times 1, 0 plus x2 times 0, 1. I just took two things that were equal and transformed both of them. But now this thing on the right-hand side, this is equal to t of x1, 1, 0 plus t of x2, 0, 1, because my rule of a linear transformation says that if I'm adding things up first and then transforming, I can change it around and transform first and then add. But now my second rule said that if I'm multiplying, I can multiply first or after. So this is equal to x1 times t of 1, 0 plus x2 times t of 0, 1. So I've used those two rules that define what a linear transformation is to just kind of alter it, change it around. But I was told what that's equal to and what that is equal to. So this is equal to x1 times 1, 4, 3 plus x2 times, I was told what t of 0, 1 is equal to. It's equal to negative 1, 2, negative 2. So I can now combine these, and this is equal to x1 minus x2, 4x1 plus 2x2, and 3x1 minus 2x2. And there's my answer. So no matter what I start with, what vector I start with, I have an equation that gives me my transformation. The entire linear transformation is defined, or we can figure it all out, just from two examples when I'm going from R2 to some other vector space. Which leads to theorem 10. If we have a linear transformation from Rn to Rm, there exists a matrix such that that linear transformation is a matrix transformation. Now, in the last class, we saw that a matrix transformation and a linear transformation were defined a little bit differently. It doesn't take a whole lot to see that a matrix transformation is a linear transformation. This goes the other way. This says if I have a linear transformation, even if I didn't give you a matrix, as soon as I know it's a linear transformation, there is a matrix. I can find a matrix where that linear transformation is the same exact thing as that matrix transformation. In other words, these two things are the exact same, even though I've defined them differently. And the second thing is, in fact, that matrix is defined by the columns of the identity matrix. In the previous example, I told you what T of 1, 0 was and what T of 0, 1 is. Notice those two vectors are the columns of the identity matrix. If I have that, that is all that I need to find my matrix. And as soon as I have my matrix, I know exactly what my transformation is, because now I can define it for everything. And this matrix has a name. If I have the linear transformation to start with, and I get the matrix, it's called the standard matrix for the linear transformation. So for example, if I have this, find the standard matrix. So this is from R2 to R3. So what I need to do is figure out what the transformation is for E1, which is the first column of my identity matrix. And E2 is the second column of my identity matrix. So now when I'm looking for the standard matrix that is associated with this transformation, all I have to do is figure out T of E1 and T of E2. Well, T of E1 is equal to T of 1, 0. And I can get that by just plugging my 1, 0 into here. I get 3, 1, 1. T of E2, well, that's T of 0, 1, the second column of the identity matrix. Plug it into my definition, I get 1, negative 1, 2. So the standard matrix associated with this transformation is equal to, take that first column, 3, 1, 1. Take the transformation, the second column is the transformation of the second column of the identity matrix, 1, negative 1, 2. That is my matrix. So notice at the start, I didn't say that I had a matrix transformation. All I said was that I have a linear transformation. That just knowing there's a linear transformation means I can get my matrix. And so this means that any transformation of a vector is equal to that matrix times that vector. What does this mean? Well, remember what the multiplication is. Multiplication of a matrix times a vector is giving you a linear combination of the columns of that vector, or of that matrix. Well, we got the columns of that matrix by applying the transformation to the columns of the identity matrix. But if we have the matrix and we're doing a linear combination of the columns, that was the definition of a span. So every possible result that you can get is a linear combination of the columns. That means the range, which is all the possible answers you can get, is equal to exactly the span of the columns. Remember, the span of the columns is all possible linear combinations of the columns. So the range of a linear transformation exactly equals the span of the columns of this matrix. So this is bringing together a couple of ideas that we've seen. Now here's a couple more ideas. A linear transformation, or this applies to a function as well, a general function, a linear transformation is onto if its range is all of Rm. An onto function means that the range is the same as the codomain. So if I take anything in Rm, no matter what the vector is, there is something I could start with to get there. We saw an example last time of something that was in the codomain but not in the range. That means that function was not onto. Onto means that no matter what you take in your codomain, you can get there. A second definition is one-to-one. One-to-one means that every pair of distinct vectors that you start with has a distinct image. So in other words, if I take two vectors in Rn, any two vectors, they will never be equal after I do the transformation. They will always transform to different things. That is called one-to-one. So this concept of onto and one-to-one is important for linear algebra. So let's take a look at one-to-one. Let's say that we have something and I tell you it's one-to-one. So it means that if I start with two different things, I end up with two different things. Since t is a linear transformation, we know that t of 0 equals 0. What does this mean? This means that nothing else can turn into 0. No matter what other vector I start with in Rn, it will never transform into 0. So the only way to get 0 is to start with 0. This should be something that sounds a little bit similar to something we've already seen. Remember that the linear transformation is the matrix, the linear combination of the columns of the matrix. Well, if it's one-to-one, that means that a linear combination of the columns can never turn into 0. We already saw this idea when it is impossible to take a linear combination and turn it into 0. That was the idea of a linear independence. So linearly independent vectors and one-to-one transformations are very closely related. This is an important concept. So it's worth spending some time on this and with some of the examples from the book to try to understand this concept. One-to-one transformations have, or any transformation has an associated matrix. If that transformation is one-to-one, that means the columns of the matrix, there's no way to combine them to get 0 unless you start with zeros. That was the exact idea behind linear independence. We have this theorem 11. If we have a linear transformation where A is the standard matrix for that transformation, then we have two things. T maps Rn onto Rm, in other words, it's onto, if and only if the columns span Rm. In other words, the range is equal to the codomain only if it's onto. That is essentially the definition of onto. And the second thing is one-to-one means you are linearly independent. It also goes the other way. If you are not one-to-one, you are linearly dependent. So not being linearly dependent means that there's a way of combining the columns to get 0. That means there's more than one way of getting 0. There are different vectors you can start with to get 0 after you transform. That means you are not one-to-one. And remember that the idea of linear dependence and linear independence were also related to whether or not you had infinitely many solutions or a single solution for a system of linear equations. So that idea is there as well. Everything we've seen so far is tied closely together. Again, the way that these things relate to each other are very important in the study of linear algebra. It is worth spending some time at this point going through the problems in the book, some of the sample problems, and trying to understand these congruences as much as possible. As an example, here's a function. Is this function one-to-one, and is it onto? Okay, let's deal with the one-to-one first. One-to-one means that no matter what two things you start with, you end up with, if you start with two different things, you end up with two different things after you transform them. That we just saw in the theorem was the same thing as saying, are the columns linearly independent of the matrix, of the standard matrix? Well, what is the standard matrix? The standard matrix for this is, well, we saw that it is the transformation of E1 followed by the transformation of E2. Well, what is the transformation of E1 and E2? Transformation of E1, remember E1 is the vector 1, 0, the first column of my identity, my 2 by 2 identity matrix. So plug 1, 0 in here, I get 1, 2, 1. My second column is the image of 0, 1 of the second column of my identity matrix, which is 2, 1, 0. And there is my A. Now, is T one-to-one? In other words, if I take my matrix augmented with zeros, am I going to be able to combine this to get a solution that is non-zero? So I take my matrix 2, 1, 0 augmented with zeros. In other words, I'm saying, can I combine these columns to get 0 without using all zeros? Row reduce. So I take 2 row 1 minus row 2 is my new row 2. 1, 2, 0, 0, 3, 0. And I'm going to do, I'm just going to do row 1 interchanged with, no. I'm going to do row 1 minus row 3 is my new row 3. Again, there's all kinds of ways of doing this. 0, 2, 0. And then I can do 2 row 2 minus 3 row 3 is my new row 3. As you do more and more row reductions, you will get faster and faster at them and more confident in them. But at this point, I have row reduced to echelon form. I have a leading entry in every column. I have my zeros at the bottom. This means that there is a single solution there, which means that there is no way of combining these columns to get 0 without multiplying each of them by 0. There is no non-trivial solution. So it is one-to-one. No matter what two vectors you start with, you are going to end up with two different vectors. The second one was asking if it was onto. So if it's onto, I'm asking if I have my augmented matrix with any x1, x2, x3, any vector, can I get that vector, x1, x2, x3? Or are there some vectors that I just can't get? Now, some of you may be able to see right away and get a very quick answer to this. But if we do the row reductions, we can also see what happens. So 2 row 1 minus row 2 is the new row 2, 1, 2, x1. We get 0, 3, 2x1 minus x2, and 1, 0, x3. I am going to now do row 1 minus row 3 is my new row 3. I get this. Zero, 2, and x1 minus x3. And I'm going to do 2 row 2 minus 3 row 3 is the new row 3. These are the same exact operations I did last time, but I just have a different augmented column. I'm going to get 0, 0. So twice that minus 3 times that. It's going to give me 4 minus 3, so it's going to give me x1 minus 2x2 plus 3x3. Now I have a leading entry in my first column and second column, that's no problem. But my third column has a leading entry in my augmented row. That means that so long as my x1 minus 2x2 plus 3x3 is non-zero, that means that there is no solution. So if x1 minus 2x2 plus 3x3 is not equal to 0, there is no solution. And it's very easy to get that. So T is not onto. There are vectors that in R3 that I can't reach. My range is not equal to my domain. That means that my transformation is not onto. Okay, so this was a short chapter, but it introduced some very, very important concepts. The connection between linear independence, between one-to-one transformations, and having infinitely many or a single solution or possibly no solution to a system of linear equations. These ideas are all tied together, and it is very important to try to understand these ideas for linear algebra. Okay, so we will not be doing section 1.9 out of the book for now. I'm going to be saving some of those things for later. So this finishes up chapter 1 out of the book.